students will be able to work on exponential functions. Exponential functions are a nonlinear function in the form of y equals ab to the x. I'll make this a little bit smaller font. Where a can't equal 0, because if a equals 0, you just have a point. So it'll be 0, 0. And b can't equal 0. B doesn't, b is greater than 0, and b doesn't equal 1. Because if you have b equals 1, it's going to be a boring function. It's going to be a linear function. So this is, what an exponential function is. This is going to be new functions you may have seen in the past, such as linear functions. So you've seen linear functions in the form of y equals, 10x plus 3. And some of you may have seen quadratic functions. Quadratic functions, which are functions in the form of, y equals 5x squared plus 6x minus 7. Those are the type of things that are quadratic functions. All right. So we're going to be starting with graphing the exponential function. Last week we talked about properties of exponents and exponent expressions. So we will start off from here. So y equals 2x squared. 2 squared equals 4. Actually, I made a mistake. 2 to the negative 2 is going to be 1 over 2 squared, which equals 1/4. 2 to the negative 1 equals 1 over 2 to the 1, which equals 1/2. 2 to the 0 is going to equal 1. 2 to the first power equals 2. 2 squared is going to equal 4. 2 cubed is going to equal 8. 2 to the 4th is going to equal 16. 2 to the 5th and equal 32. 2 to the 6th is going to equal 64. So we need to graph the exponential function using the table, and then we're going to determine the domain and range, and we will describe the behavior of the graph. We're going to graph them using different colors. So now that I have my first one, I will start my graph using this color, so the color purple. Okay, so going to graph here. So I started with x equals -2. So x equals -2. And I was at 1/4. -1, which was 1/2. Then I have x equals 0, which was about 1. X equals 1, which is about 2. Now I have 2. 2 squared is 4. 2 cubed is 8. Wow, this is really interesting. So 4.5 to about 1 to 2 to 4 to 8 to 16 and this is growing. 16. Now 5 is going to become 32. And this is growing very quickly. And yeah, and that's it. So then this thing, if we keep going, sorry for that. Graphing this thing is not fun on the computer. So then connect the dots. Connecting the dots. Connecting the dots, connecting the dots, connecting the dots, and boom, it has this type of graph. So let's see what happens, because it keeps growing quickly. So let's see what happens. So this thing has, let's take a look at its domain. In terms of domain, this thing starts, looks like it'll keep going all the way. So the domain starts at negative infinity, and then it looks like it could go all the way up because this thing grows very quickly to positive infinity. Now let's take a look at our y-intercept. The y-intercept happens when x equals 0, and that is when x equals 0, this guy is 1. The x-intercept is a point, or the y-intercept is a point. The range, if we take a look at the range, this thing starts at 0, but it doesn't include 0, so we're going to use a parenthesis. And it goes from 0, and it goes all the way up to infinity. So the behavior is as x increases, y increases. Let's take a look at the second graph. 3 times 2 to the x. So we already did all the work for 2 to the x, so now we're just going to be moving forward with just, multiply the value in front of it. So we'll start off here. 3 times 2 to the negative 2 is going to be 3 over 4. 3 times 2 to the negative 1 equals 3 over 2. 3 times 2 to the 0 equals 3. 3 times 2 to the 1 equals 6. 3 times 2 squared is going to be 12. 3 times 2 cubed is 24. 3 times 2 to the 4th is going to be 48. 3 times 2 to the 5th is going to be 96. 3 times 2 to the 6th is going to be 192. And that's not the y-intercept, my bad. So let's graph this thing and then we'll figure out the y-intercept. I'm actually going to use the color blue for this graph. Blue. So then we start off with 3/4. 3/4 for negative 2. 3/4 would be about here-ish. And then, actually 3/4 would be more about here. 3/4 would be, 3/2 would be about here. 3 would be about here, because when x equals 0, y was 3. When x equals -1, it was 3/2. When x equaled -2, it was 3/4. X equals 1 gives it a value of 6. X equals 2 gives it a value of 12. X equals 3 gives it a value of 24. X equals 4 would be, I believe, 48, and we don't even have that much room for our graph here. So now let's connect the dots. So then this thing will just starts at 0. And then it goes all the way up. And then it increases like this. Sorry for the poor graph. Then let's go to the next one. Negative. Okay, so the y-intercept is 0, 3. The domain is the same. It goes from -infinity to +infinity. The range still stays the same. Looks like it started at 0 and went all the way to infinity. Then the behavior looks like as x increases, y increases. Now let's take a look at this function right here. Will this one be green? And let's see. Again, we did the legwork already. So -3 times 2 to the -2 is going to be -3/4. -3 times 2 to the -1 equals -3/2. Then we have -3 times 2 to the 0, which is -3. Then -3 times 2 to the 1 equals -6. -3 times 2 squared is -12. -3 times 2 cubed is going to be -24. And if you figured out the pattern, this thing doubles every time. So then, let's see, -48. Or it's the same thing as the one next to it, -96 and -192. 3, -3. 2 to the 4th, -3 times 2 to the 5th, -3 times 2 to the 6th. Again, we're going to graph this guy in green. -2, comma, -3/4. -2, comma, 3/2, or -1, comma, 3/2, 0, comma, -3, 1, comma, -6, 2, comma, I believe -12, 3, comma, 24. I'll scroll down. 3, comma, 24. And that's about all I could get on this graph. Connect that. And then you get this graph that looks like this, that's in green. And the y-intercept is 0, -3. The domain is -infinity to infinity. The range is actually quite different for this one. And the range is actually going to be from -infinity to 0. This thing never quite reaches 0, but it never quite touches 0, but it tries to reach it, but it never does. And the behavior is as x increases, y technically it decreases actually, because you're getting bigger and bigger negative numbers. But it still has a huge amount of exponential. The growth is huge, and that's why it's called exponential growth. Do and work on exponential functions, day 1, part 2, exponential growth. So right here, as you could tell, I have my exponential growth function right here, y equals a times the quantity 1 plus r raised to the t. So the t, as you know, stands for time. R is the growth rate. And that's how much it's going to like, well, that's like the percentage it would increase by. Again, growth means it's going to increase, get bigger. So this A right here is the initial amount. And the 1 plus R right here, this entire thing right here is, I'm going to highlight it. So this part right here that I'm highlighting, this part right here, which got highlighted, that's what is known as the growth factor. Man, those planes are loud. Okay. So that y-intercept, I know for the y-intercept is that x equals, or x or t will have to equal 0. In this case, it'll be my 0, comma a. My x-intercept, if we reflect back on yesterday's notes, is when the graph crosses the x axis, and that doesn't happen with this function, only in special cases with vertical shifts, but we're not going to talk about that yet. We might not talk about it in this course. So there is no x-intercept. There's none. Is there more? No, that's it for that part. Next page of notes. We're going to talk about some of the patterns we see. So linear functions have a pattern where you add the same number each time. So for me to get from 0 to 5, I have to add 5. Boom. 5 to 10 plus 5, boom. 10 to 15 plus 5, boom. 15 to 20 plus 5, 20 to 25 plus 5. And, linear patterns have that same pattern where you add the same amount each time. Some of you may have heard of quadratic functions. Some of you may not have heard of quadratic functions. So quadratic functions, you've taken my advanced algebra course, quarter 2. You might have covered it with me. If I had more time and before COVID would have happened, I would have covered them. I've covered quadratic equations in the warm-ups, but not the functions. Anyway. It kind of makes like a U-shaped pattern. Or the pattern follows an interesting pattern. So 3, 1, 1, 3, 5. The pattern that it follows does eventually looks like it becomes, for this one would become a 2, but it follows like a 1, 3, follows a 1, 3, 5, 7, 9 type of pattern, or a factor of, the 1, 3, 5 pattern. And exponential functions follow a different type of pattern. It's called exponential. You got to look at the pattern. So the pattern is, so it goes from 3, 6, 12, 24, 48, but that doesn't seem like that would actually be the pattern. Looks like that there's a different type of pattern. So how would I get from, so adding doesn't work because that doesn't seem consistent. So how do I get from 3 to 6? Multiplied by 2. How do you get from 6 to 12? Multiplied by 2. How do I get from 12 to 24? Multiplied by 2. So it looks like this guy has a multiply by 2 pattern. And that's how you know it's an exponential. You know it's an exponential function if the pattern is achieved by multiplying the same number repeatedly versus other functions where you'd have to add to get the pattern. And I'll do some more examples, and I'll do some examples of how to write, function. Next slide. Write a rule for the function. So to do that in the function rule, we know that it's a function in the form of y equals a times b to the x, or y equals ab to the x. So what I do is I look for the pattern first. So from here to here, you multiply by 2. Because from 8 to 16, you get from 8 to 16, you double it. You get from 16 to 32, you double it. That's what I did. How do you get from 2 to 4? You multiply by 2. Or you could do the opposite. You multiply by, from here to here, since you're going down, you divide. Divide, divide, divide. So I know that I keep having to multiply by 2. Now, the thing is, I need to find my a value. My a value is my starting value. So when x is 0, what's y going to be? So a is the starting value and if a equals 8, so if when x is 0, y is 8, then that means a is going to be 8. And my b value is the pattern. B value is my pattern. So I'm going to multiply by 2 each time. So therefore, my function is going to be y equals 8 times 2 to the x for the first one. Now, I'm going to move on to number 2, which is this. So first thing I'm going to look is at my starting value. So when x is 0, y is 27. So that is my starting value. That is my y-intercept. So, the starting value is 27. So A is 27. Now I got to look for my pattern. How do I get from 3 to 9? By adding plus 6, plus 18, plus 54. So there's no real adding pattern. Could I multiply to get here? Let's test it out. How do I get from 3 to 9? Multiplied by 3. How do I get from 9 to 27? Multiplied by 3. 27 to 81. Multiplied by 3. 81 to 243. Multiplied by 3. Now, I did that. So that's my pattern. You multiply by 3. So my starting value is 27, and my pattern is, times 3. So then it's just going to be y equals 27 times 3 to the x. That's it for that one. Number 3, what's my starting value? My y-intercept or my starting value is going to be 0, 16, because when x is 0, y equals 16. Now I got to look for my pattern. So I get from 1 to 4. With addition, you'd add 3 plus 12 plus 48. Doesn't give me a consistent pattern, but it looks like it follows a pattern of multiplication. So from 1 to 4, use times 4. 4 to 16, use times 4. 16 to 64, use times 4. Down, you use times 4. So I have my starting value. I have my pattern, which is times 4. Remember that y equals a times b to the x. If my a or starting value is 16, and my b value or my pattern value is 4, it's going to be y equals 16 times 4 to the x. And that's it for that one. Now let's practice some word problems. Example 4. The price in dollars of a pound of flour was 27 cents in the year 2000. The price has increased by about 2% each year. Let T be the number of years since 2000. So the first question is, write a function that models the value of the car over time. The second question is, what will the price be in the year 2020? Hey, that's this year. So first thing we're going to do, we're going to answer A. So we know we're going to look for the starting point. So the starting value is 27 cents. And we got that from reading the problem. Then we're going to look at our growth rate. The growth rate is 2%, which, if you change the percent to a decimal, there's going to be 0.02 or 0.02. Then we have to use our exponential growth equation, which is y equals a times the quantity 1 plus r, which is our rate. So y equals our starting value times 1 plus our rate raised to the t, or raised to the amount of time, where t is time per year. You know that t is time per year. And the thing is, this 1 represents, the starting value, because you need that starting value plus the rate it's going to increase each time. Because if you don't include it, you're just going to be multiplying 27 cents times 0.2, and that's going to imply that the price is going down, when in fact the price of flour is actually going up. So now I'm going to rewrite my equation. So I have y equals my starting value, which is 27 cents or 0.27, times 1, which the 1 represents you keeping your starting amount, plus my growth rate, which is 0.02 or 0.02. And this whole thing right here is going to be my growth factor raised to the time function, which is going to equal 27 hundredths or 0.27 times 1.02 to the t. And that's my equation, or my function. Now they're asking, what will the price be in the year 2020? So here's the thing. So remember, it is years since 2020. So 2020 would be represented by the value or the year 0, not by the year 2000. So from 2000 to 2020, that is a total of 20. So your t value is going to be 20. So t is going to equal 20. Now we need a calculator. I have my calculator function right. 1.02, 1 and 2 hundredths. See if it does this. Oh, it does. Raised to the 20th power. And the price of flour rises to, well, actually, the price of flour will rise to, using my function, 0.27 times 1.02 to the 20th power equals 40 cents per pound of flour in the year 2020. And I don't think flour is 20 cents per pound. I'll look that up later. All right. The last example, example 5. The owner of a 1953 Hudson Hornet convertible sold at an auction. The owner bought the car in 1984 when its value was $11,000. The value of the car increases at a rate of 6.9% per year. Write a function that models the value of the car over time. That's the first question. The second question is, the auction took place in 2004. What is the approximate value of the car at the time of the auction? Round your answer to the nearest dollar. So the first thing we need to do is write the function. So a function, when you're given a starting value, a starting amount or initial amount, and a percent increase, you're going to use the function, the exponential growth function, which is going to be y equals a times the quantity 1 plus r raised to the t. So let's take a look at our starting amount. So we know that the initial value or starting value at the auction, the starting value in 1984 was A is initial value is $11,000. We know that the rate that it increases per year, so R is the growth rate, per year, 6.9%, or as a decimal, places to the left, 69 thousandths. Then we need time. T is time in years. So now I can put that together to write my function. So y equals my starting amount times my growth factor raised to the amount of time, which is going to be y equals my starting amount or initial amount is 11,000 times 1 plus my growth rate, which is 0.069 or 69 thousandths to the time in years, which is going to be my function that models the car growth or the value of the car over time. Now B asks me for the value of the car at the time of the auction. So the starting was in 1984. So since 1984. And then we get from 1984 to 2004. So that's 20 years. So my time is going to be, T is going to equal 20 years. So if T equals 20, I'm going to have to plug in Y equals 11,000 times 1 plus, or no, I lied. Jump to the gun here. 1.069 to the 20. Actually, I didn't finish this problem up here. 1.069 to the T. I'm going to bring out my calculator to calculate that. And I do that, I get 11,000. $1.069 to the 20. And because it's been 20 years since 2004, and I get $41,777.92. cents as my final answer.